Hi everybody. In our last lecture, that is lecture number 9, we had completed up to 45 number question. This is the 45 number question. So in today's lecture, let's start from 46 number question. So this is the 46 number question. The question is like this. For momentum space, the wave function psi pt, the Schrodinger equation is written as what? So let's see the solution. This is the solution. We know the Schrodinger equation, h psi equal to e psi. This right hand side we can write, we can put the Hamilton's operator I is equal del dou psi by dou t, and the right hand side we can write in the form of kinetic energy and potential energy. And we also know that the potential energy is a function of a position. So what you need, we don't need to change this kinetic energy term because already contains the momentum term. Okay, so what you need, we need to change this position term. So in the momentum space, how can you write the position operator? We can write this position operator as like this. You see in the bottom, x cap can be written as I is cut dou p by dou p. So you simply put here in the space of x cap, and you simply do some calculation like multiply I in the numerator and denominator, and you will get minus I minus s cut by I dou by dou t. Okay, so option D is the correct one. Option D is the correct one. Sorry, option C is the correct one, not D. Okay, option C is the correct one. Now coming to the option number, question number 47. The 47 number question is stated like this: choose the wrong statement. Okay, so read all the options one by one. Option A has stated that any set of mutually orthonormal function is linearly independent. Okay, this is a correct option. Why? Let's see the solution. Because let's take any two function psi1 and psi2, and if you find that these two wave function are mutually orthonormal, that means we can write this anyone among the function in the term of a scalar multiplier of the other function. So that means what? These both functions are linearly independent. That's why you can write. Okay, so if we both any one of this, if these two functions are dependent with some multiplication of a scalar, then we can, at that time we can call that these two wave functions are linearly dependent. But as these two wave functions are mutually orthonormal, that means they are giving you, if you make the scalar product, that obviously they will give you 0. Okay, so we can write it in the form of in a linearly, they are linearly independent. So that's why this option is correct one. But we have to choose the incorrect statement. So option B, let's come to option B. Q is called as observable if it is represented by a Hermitian operator Q and possesses a complete set of eigenfunction. This is also a correct one. Why? You see, oh, I have not written, but you see, in quantum mechanics, if you want to make any observable as a operator, that operator should be a Hermitian operator. And to becoming a Hermitian operator, there are some criteria. What are those criteria? Like the criteria is uh, when this any operator, that is any Hermitian operator, operates on a wave function, it will give the a real eigen value. Okay, and as well as it possesses a complete set of eigenfunction. Okay, so those are the property, and option B is the correct one. Now coming to the option C. Option C is a complete measurement of a state psi implies the determination of all probability amplitude. It is also a correct one, because whenever in quantum mechanics we want, we 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 find any probability of any wave function, what do you do? We do, we first normalize that wave function and we make them, then we take the inner product. Okay, and inner product square. Okay, so what you do, we do this inner product for every component of that standard wave function. That means if that wave function is a superposition of any other basis or state, then we have to normalize, or we have to find the uh, component square. Okay, so we have to add all those components, then we can find the probability. Okay, so that's why option C is the correct option. But if you see the option number D, the option number D is the set of functions psi n r, which are not orthonormal and complete, do not possess closure property. Now you see that there are, it is mentioned three properties here. One is orthonormal, the other is completeness, and the third one is closure property. Now you see one by one what are those property meant by. Orthonormal property. Orthonormal means if you make the scalar product, okay, or the inner product, it will give you 0 or 1. If it gives you 0, if it gives you 0, then it is orthonormal. If it is not give you 0, then it is 1. Okay, this is the orthonormal property. Now what is completeness? Completeness means we can write if you take any wave function from the Hilbert space, and we can write that wave function in the form of a complete set of orthonormal bases. That means it is a that means it is possessing that completeness property. And what is closure property? Closure property means if you take the cat's eye and brass eye, and if you add those, it will give you what? A unitary operator. Okay, now if you see this completeness property, for an example, I have given an example in the vector form, like 2i cap plus 3j cap plus 5 cap k cap. To write this vector, we need three bases, that is I cap, j cap, and k cap. And in quantum mechanics, we write it as 0 1 0 0 0 1 0 and 0 0 1. Okay, so if you want to write any 4-dimensional vector, then what you need? We need 4 bases. In 3 dimension we need 3 bases, like this. Okay, so if you want to know more about this closure property, I have given an example in the last. You can see this is the example. Here I cap is the 1 0 0, like this. And if you want to find the closure property is satisfied or not, then you do like this. You multiply this vectors, column vectors and row vector by the help of the matrix property, and you will get this matrix, and it is nothing but a unitary operator. Okay, this is the closure property. Now coming to the 48 number question. The 48 number question has asked the Hamiltonian of a free particle. Hamiltonian of a free particle means there is no potential term, only kinetic energy term is present. Now if the potential energy term is 0, that means the Hamiltonian term is equal to p square by 12. And any vector, any operator in quantum mechanics is a Hermitian operator. Okay, and it is a linear operator. So that's why option number A is the correct one. Okay, this is the correct option. Option number A is the correct option. And if you want to know what is linear operator, this is a condition of a linear operator. If that operator satisfies this condition, where this A and B are two scalar, that may be a real function, that may be a complex function, anything. Okay, and this is the property of a associative and distributive property. Okay, so option A is the correct one for 48 number question. Now 49 number question is easy. It is given that the incident particle energy is 10 electron volt, and the potential step has a 715 electron volt height. Okay, and we have to find the reflection coefficient. So what we have to apply just the reflection coefficient function formula. Okay, this is the formula, and you put all those value and get this answer, and the answer is 0.11. Now coming to the 50 number question, the question has stated that in the case of a Heisenberg picture in quantum mechanics, okay, we have to choose the correct one. Okay, the state are not fixed. In Heisenberg picture, the state are not fixed. That means the state are time dependent. But in Heisenberg picture, the state are not time dependent. They are fixed. Okay, they are not evolved in time. That means they are fixed. But it is stated that they are not fixed. So option A is a incorrect statement. Now coming to the option number B. The option number B is the expectation value of a time independent operator on a state that varies with time cannot be written as a expectation value of a time varying operator in the time independent state. Okay, so to know this option properly, let's see option B. It is stated this statement, the option number B has stated. That means this cannot be equal to this. Now let's see one by one. Let's pick the LHS side. That means this side. So what is this side? Psi xt A operator. That means we are just calculating the expectation value, where this A is a time independent operator. Okay, but we we can write the ket psi as psi xt e to the power minus iet by s cut. We can write. Okay, now we put this value here in the in this form. When you put, you see that this e to the power iet by s cut and e to the power minus iet by s cut both will be cancel out, and ultimately you will get psi x a naught. That means at t equal to 0. That means when there is no evolution of time is present at the initial state, we will get this. And now pick the right hand side. This is the left hand side, and now pick the right hand side. Right hand side is this. The wave function is a time independent function, but the operator is a time dependent. Okay, now what you do, we see that we can write this operator in the form of a unitary operator. Okay, this is the form. Okay, now what you need to do is you just substitute this at value here in this form. Now when you substitute and you calculate, this operator operates on this, and this operator, unitary operator, operates on this. So after operating, they will give E and E. This is scalar, and in both sides they will be cancelled out, and you will get the same equation, same term, that is this. That's why this is going to be equal, not equal. But in the option number B, it is stated that this is not equal, but we are getting that this is equal to this. That means option number B is incorrect. Okay, now coming to option number C, it is stated that the variation of the observable A with time is determined by equation this, dA by dt equal to I s cut commutation of h at. Now we know that the time evolution of any operator, we can write it in the form of I by s cut commutation of that operator with respect to the Hamiltonian operator plus dou by dou t of that operator. But there is a condition here. What is that condition? If that operator is not an explicit function of a time, that means in the form of this operator, there is no time term present. In that condition, we can say that this operator is not an explicit function of time. That means no time term is explicitly visible in that expression. So at that condition, we can write dou by dou t as 0. Okay. So if you put 0 in this equation, what you will get? You will get the this equation. Okay. So one kind, in one sense this option is correct. Okay. In one sense this option C seems to be correct. Okay, because it has imposed a condition here. This is not the standard equation, remember. But in option D, if you see, it is stated that we can write a operator which is a time dependent in the form of a e to the power I s h t by s cut. This is not equal because we have just seen that form. What is that form? This is the form. You see, this is the form. How we can write it? We can write it u dagger u a u dagger. That means there are two unitary operator here, but in the option it is mentioned only one operator here, that is e to the power I s cut t by s cut. E to the power I h t by s cut. Only one unitary operator is present. So that's why option D is the incorrect statement. So this is the option C is the correct one. Okay, thank you.